Improving nuclear power plant reliability and productivity requires advanced, cost-effective, and actionable information on plant conditions. Advanced online monitoring technologies are needed to enable more effective management of aging power plant assets. Operational costs must be competitive, or a plant's long-term viability may be limited. Some of the nation's nuclear plants have recently announced early retirement as the result of load growth limits, alternate production options, and technical factors. The Electric Power Research Institute is working together with the Department of Energy's Idaho National Laboratory to address these issues and to assure the long-term operability of the nation's nuclear plants.
Well, I think the nuclear power industry is very enthusiastic about online monitoring technologies. It affords the ability to see into plants and plant processes all the time in ways in which humans simply can't. Using the senses that we have and using our physical locations are, quite frankly, limitations. And so having online monitoring technology affords the ability to see into the active electromechanical components, how they're performing, what's happening in real time, 24/7, as well as in the future to be able to monitor those large physical passive structures, concrete, metals, cables, those types of things. So it's one of the real game-changing avenues, I think, that this R&D pathway affords. And working with an organization like the Electric Power Research Institute ensures that the technology is properly suited to be deployed and is focused on the right set of issues and challenges that the nuclear power fleet faces today and will face in the future.
The Long-Term Operations Program focuses on the safe, productive operation of the nation's nuclear power plants for the next 20 to 40 years. Our monitoring technology provides early problem detection and diagnosis before damage accumulates, affecting the remaining useful life and reliability. When using this technology, the task of engineering fundamentally changes from that of data collection and problem identification to problem solving. The technology has high-value applications to all power production facilities and has been developed by EPRI's Nuclear and Generations Division.
Several utilities have deployed monitoring and diagnostic programs for fleet-wide monitoring of their critical assets. These programs provide early detection of abnormal conditions. However, the process of identifying underlying problems still relies on the knowledge of the available staff and often requires other supporting information. EPRI has developed an advisory software system to help plant response teams troubleshoot and resolve equipment problems quickly and effectively. The advisory software system identifies the possible causes of abnormal behavior based on a library of known failures or fault signatures for power plant equipment. When an advanced pattern recognition model detects changes in equipment behavior indicating a problem, EPRI's Fleet-Wide Prognostics and Health Management Suite, commonly referred to as FWPHM, combines this information with other plant information to determine the most likely cause for the change in behavior. The FWPHM software supports diagnostics, troubleshooting, and estimating a risk-informed remaining useful life of plant assets. The following demonstrations will focus on the Diagnostic Advisor module of the suite and its role in the troubleshooting process. The first demonstration centers on diagnosing degradation of the primary winding insulation, a common failure mode in a generator step-up transformer. When the transformer's primary winding insulation degrades, dissolved gases are created in the transformer's insulating oil. The type, concentrations, and ratios of gases are used to distinguish insulation degradation from other faults. Simulated faults were introduced into operating data, obtained from an in-service transformer equipped with an online gas analyzer. SureSense pattern recognition software monitors the data and creates alerts when relative concentrations of acetylene, carbon monoxide, and carbon dioxide to carbon monoxide ratio exceed recommended levels. An early indication of high acetylene concentration in the transformer's insulating oil is detected and logged. The pattern recognition software provides immediate detection of the problem based on IEEE recommendations. The Diagnostic Advisor is scheduled to check its online data sources periodically to discover new warning events. When a new event is detected, the Diagnostic Advisor runs analysis and creates a new diagnostic result and simultaneously notifies responsible personnel with an email. A diagnosis result begins with the possible diagnosis. The Diagnostic Advisor determines which diagnosis is the best match to the available plant data. Given only the alert for increasing acetylene concentration, the electrical winding insulation degradation is the only diagnosis. As monitoring continues, an increase in carbon monoxide level is observed. The Diagnostic Advisor recognizes the change automatically and updates the diagnosis result with this new information. Notice that updated information causes a new possible fault to appear: thermal winding insulation degradation. As carbon monoxide continues to increase, the ratio of carbon dioxide to carbon monoxide decreases below the recommended level, creating an additional alert. The alert is observed by the Diagnostic Advisor, updating the previous diagnostic results. Due to the evolving symptoms, thermal winding insulation degradation is now identified as the most likely fault. This demonstration highlighted the ability of the Diagnostic Advisor to combine multiple fault features to provide the most complete fault diagnosis possible. As the degradation evolves, the Diagnostic Advisor updates the diagnosis results. The second demonstration centers on diagnosing problems in a diesel engine within an emergency diesel generator system. It is essential that these engines start and run reliably because the emergency diesel generator provides power to operate the plant when the external power grid is not available. Proper engine valve timing is essential for the engine to start and meet its load requirements. Cylinder temperatures in the engine can be used to diagnose problems with the valve timing and other common faults. The demonstration uses operating data from a 24-hour run of an emergency diesel generator. Simulation was used to mimic improper valve timing. The engine parameters are monitored and the alerts are created when the temperature range between the cylinders exceeds the recommended levels, or when one or more cylinders becomes too hot. The Diagnostic Advisor detects the newly indicated problem and creates a new diagnosis result for the diesel engine. Based on the available data, both improper valve timing and degraded fuel oil supply pump are indicated as likely faults. The diagnostic result can be opened for review. The engineer in charge can input additional information by updating the open diagnosis. Entering the information that a maintenance action was performed very recently modifies the diagnosis to more strongly support the improper valve timing fault. This demonstration highlighted the ability of the Diagnostic Advisor to take advantage of all information that might influence a diagnosis, including information from periodic inspections and maintenance actions. Many utilities are proactively improving productivity and protecting operating life of their most critical assets using advanced monitoring and diagnostic technology. EPRI's fleet-wide prognostics and health management suite software is the next generation of online monitoring capability available for use in the power generation industry. EPRI will collect fault signature knowledge from across the industry, creating a database of pooled information that will mitigate the cost and effort to implement the software across the fleet of power plants. More information can be obtained by contacting your EPRI program manager.